To estimate soil resistivity for a duct bank, several factors must be taken into account. Firstly, soil type. Sand saturated with water typically exhibits a resistivity ranging from 200 to 500 cm. Moist soil, conversely, presents a higher resistivity, potentially reaching up to 10,000 cm. Secondly, water content. Saturated soil demonstrates a lower resistivity compared to dry soil. The presence of water-infiltrated conduits contributes to an overall reduction in resistivity. Thirdly, compaction. Compacted soil tends to have a lower resistivity than loose soil due to the closer packing of particles, facilitating better electrical conductivity. When conduits are infiltrated with water, it suggests the surrounding soil is either damp or very damp, especially if it has been compacted with water. Therefore, a reasonable estimate for resistivity in this scenario would be approximately 60 cm, corresponding to damp soil conditions. Remember, this figure is an estimate. The actual resistivity may vary based on specific site conditions. Conducting field measurements is always recommended to obtain the most accurate resistivity value for the duct bank's location. The resistivity of soil is a measure of its resistance to electrical current. It is an important factor in the design of electrical grounding systems, as it affects the amount of current that will flow through the ground in the event of a fault. Soil resistivity is affected by a number of factors, including soil type, moisture content, temperature, and the presence of dissolved salts. Soil type is the most important factor affecting soil resistivity. Sandy soils tend to have a high resistivity, while clay soils tend to have a low resistivity. This is because sandy soils have larger particles and more air spaces than clay soils. The larger particles and air spaces impede the flow of electrical current. Moisture content also affects soil resistivity. As the moisture content of the soil increases, the resistivity decreases. This is because water is a good conductor of electricity. Temperature also affects soil resistivity. As the temperature of the soil increases, the resistivity decreases. This is because the water in the soil becomes more conductive at higher temperatures. The presence of dissolved salts also affects soil resistivity. As the concentration of dissolved salts in the soil increases, the resistivity decreases. This is because dissolved salts are good conductors of electricity. There are a number of methods that can be used to measure soil resistivity. The most common method is the 4-point Wenner method. In this method, 4 electrodes are placed in the ground in a straight line. A current is passed through the 2 outer electrodes, and the voltage is measured between the 2 inner electrodes. The soil resistivity can then be calculated using the following formula: ρ equals 2 pi of V divided by I, where ρ is the soil resistivity in ohmmeters, is the spacing between the electrodes in meters, V is the voltage in volts, and I is the current in amps. Soil resistivity is an important factor to consider when designing electrical grounding systems. A low soil resistivity is desirable, as it will allow more current to flow through the ground in the event of a fault. This will help to protect people and equipment from electrical shock. There are a number of things that can be done to reduce soil resistivity. These include adding water to the soil, adding dissolved salts to the soil, and compacting the soil. The choice of which method to use will depend on the specific site conditions. Estimating soil resistivity for a duct bank installation is crucial for ensuring the safe and efficient operation of underground electrical systems. Soil resistivity, denoted as ρ, dictates how easily electric current flows through the ground. This directly impacts the performance of grounding systems designed to protect equipment and personnel from electrical faults. Several factors influence soil resistivity, requiring a comprehensive approach to estimation. Soil type is a primary determinant. Sand, particularly when saturated with water, typically exhibits a resistivity range of 200 to 500 cm. This relatively high resistivity stems from the larger particle size and greater air gaps within sandy soil, hindering the flow of electric current. In contrast, clay soils generally possess lower resistivity due to their finer particles and higher water retention. Moisture content plays a significant role. Increased moisture levels invariably lead to decreased soil resistivity. Water is an excellent conductor of electricity, facilitating current flow through the soil. Saturated soil, therefore, offers the least resistance to electrical current. Compaction also affects soil resistivity. Compacted soil, with its denser arrangement of particles, exhibits lower resistivity than loose soil. The close proximity of particles enhances electrical conductivity. Temperature has a more subtle influence. Higher soil temperatures typically result in slightly reduced resistivity, as the water within the soil becomes more conductive at elevated temperatures. Dissolved salts, if present in the soil, significantly lower resistivity. Salts act as electrolytes, greatly improving the soil's ability to conduct electricity. The presence of water within conduits, as indicated, strongly suggests damp or very damp soil conditions, particularly if the surrounding soil has been compacted with water. Given these circumstances, a reasonable estimation for soil resistivity would be approximately 60 ohm-centimeters, aligning with the characteristics of damp soil. However, it is crucial to acknowledge that this is an estimation. Actual soil resistivity can vary considerably depending on specific site conditions, geological factors, and localized variations in soil composition and moisture content. For accurate determination of soil resistivity, conducting on-site field measurements is highly recommended. Standard methods, such as the 4-point Wenner method, provide reliable data for grounding system design. The Wenner method involves inserting 4 electrodes into the ground in a linear configuration. A known current is passed between the outer electrodes, and the resulting voltage drop between the inner electrodes is measured. Using these measurements and the spacing between the electrodes, soil resistivity can be calculated. The formula for calculating soil resistivity using the Wenner method is ρ equals 2 pi V divided by I, where ρ is the soil resistivity in ohm meters, is the spacing between the electrodes in meters, V is the voltage in volts, and I is the current in amps. Alternative methods for measuring soil resistivity include the Schlumberger method and the dipole-dipole method, each with its own advantages and disadvantages depending on site conditions and required depth of investigation. Soil resistivity measurements are essential for several key applications in electrical engineering. Firstly, grounding system design. Accurate soil resistivity data is critical for designing effective grounding systems that ensure the safe dissipation of fault currents, protecting personnel and equipment from electrical hazards. Secondly, cable routing. Soil resistivity influences the thermal properties of the soil, impacting the heat dissipation capabilities of buried cables. This information is crucial for determining appropriate cable spacing and ampacity ratings to prevent overheating and ensure reliable operation. Thirdly, corrosion control. Soil resistivity is an important factor in assessing the corrosive potential of soil environments on buried metallic structures such as pipelines and grounding electrodes. Higher resistivity soils tend to be less corrosive. Knowledge of soil resistivity helps in selecting appropriate corrosion protection measures. Fourthly, electromagnetic interference mitigation. Soil resistivity affects the propagation of electromagnetic waves, influencing the levels of electromagnetic interference experienced by underground cables and equipment. Understanding soil resistivity helps in designing effective shielding and grounding strategies to minimize interference. In summary, estimating soil resistivity for duct bank installations requires a careful consideration of soil type, moisture content, compaction, temperature, and the presence of dissolved salts. While estimations based on general soil conditions can provide a preliminary assessment, conducting on-site field measurements is essential for obtaining accurate data necessary for the safe and reliable design of electrical systems. The 4-point Wenner method is a widely used technique for measuring soil resistivity. It involves 4 electrodes placed in the ground in a straight line, with equal spacing between them. A current is injected into the soil through the 2 outer electrodes, and the voltage drop between the 2 inner electrodes is measured. The soil resistivity is then calculated using the formula previously mentioned. The accuracy of the Wenner method depends on several factors, including the spacing between the electrodes, the depth of the electrodes, and the uniformity of the soil. The spacing between the electrodes should be at least 3 times the depth of the electrodes. The depth of the electrodes should be at least 1/20th of the spacing between the electrodes. The soil should be uniform in the area surrounding the electrodes. If the soil is not uniform, the Wenner method will not provide an accurate measurement of soil resistivity. In this case, other methods, such as the Schlumberger method or the dipole-dipole method, may be more appropriate. The Schlumberger method is similar to the Wenner method, but it uses a different electrode configuration. The dipole-dipole method uses 2 electrodes to inject current into the soil and 2 electrodes to measure the voltage drop. The dipole-dipole method is more sensitive to changes in soil resistivity than the Wenner method or the Schlumberger method. However, it is also more difficult to interpret the data. Once the soil resistivity has been measured, it can be used to design electrical grounding systems to determine appropriate cable spacing and ampacity ratings to assess the corrosive potential of soil environments and to mitigate electromagnetic interference. Electrical grounding systems are designed to protect people and equipment from electrical shock. A good grounding system will have a low resistance to ground. This will allow fault currents to flow quickly to ground, tripping a circuit breaker or fuse and preventing electrical shock. The resistance to ground of a grounding system depends on the soil resistivity, the size and shape of the grounding electrodes, and the number of grounding electrodes. Cable spacing and ampacity ratings are determined by the thermal properties of the soil. The soil acts as an insulator, preventing heat from escaping from the cable. If the cable is too close to other cables or to the ground surface, the heat will not be able to dissipate properly, and the cable will overheat. Overheating can damage the cable and can even cause a fire. The ampacity rating of a cable is the maximum amount of current that the cable can safely carry. The ampacity rating depends on the size of the cable, the type of insulation, and the ambient temperature. Soil resistivity is an important factor in assessing the corrosive potential of soil environments. Soil corrosion is a chemical process that can damage buried metallic structures. The rate of corrosion depends on the soil resistivity, the moisture content, the pH, and the presence of dissolved salts. Electromagnetic interference is unwanted electrical noise that can interfere with the operation of electronic equipment. Soil resistivity affects the propagation of electromagnetic waves. Understanding soil resistivity helps in designing effective shielding and grounding strategies to minimize interference. The estimation of soil resistivity, while often simplified to a single value, is in reality a complex undertaking that benefits from an understanding of the various factors contributing to its determination. Soil composition, including the types and proportions of sand, silt, clay, and organic matter, fundamentally shapes the soil's electrical properties. Water content, a highly dynamic variable, significantly alters resistivity, with saturation leading to substantially lower values. Temperature, while less dramatic in its impact, still plays a role, influencing ion mobility and thus conductivity. The presence of dissolved salts, acting as electrolytes, dramatically enhances conductivity, especially in arid regions or areas with industrial contamination. Compaction, by reducing pore space and increasing particle contact, generally lowers resistivity. Soil structure, encompassing the arrangement of soil particles into aggregates, affects both water retention and aeration, indirectly influencing resistivity. Geological history and local geological formations contribute to the overall soil profile and its inherent electrical characteristics. Seasonal variations in rainfall, temperature, and groundwater levels cause temporal fluctuations in resistivity. Depth also matters, as soil properties often change with depth, leading to variations in resistivity at different levels below the surface. Site-specific conditions, including drainage patterns, vegetation cover, and human activities, can further modify resistivity. Considering the presence of water-infiltrated conduits, the resistivity estimate of 60 ohm-centimeters is a reasonable starting point. However, this should be regarded as a preliminary value, subject to refinement based on detailed site investigations. Employing techniques such as the 1 or 4-point method, supplemented by laboratory analysis of soil samples, provides a more comprehensive and reliable assessment. Moreover, continuous monitoring of soil resistivity over time can track seasonal variations and identify potential long-term changes. The presence of utilities and buried infrastructure should also be taken into account, as they can influence local soil conditions and electrical properties. In addition to the factors already discussed, the type of backfill material used around the duct bank can also affect soil resistivity. If the backfill material is different from the surrounding soil, it can create a localized area of higher or lower resistivity. This can affect the performance of the grounding system and the thermal properties of the soil. Therefore, it is important to select a backfill material that is compatible with the surrounding soil. Furthermore, the presence of any nearby metallic structures, such as pipelines or fences, can also affect soil resistivity. These structures can act as conductors of electricity and can alter the flow of current through the soil. Therefore, it is important to take these structures into account when estimating soil resistivity. Finally, it is important to note that soil resistivity can vary significantly over time. This is due to changes in moisture content, temperature, and other factors. Therefore, it is important to measure soil resistivity at different times of the year to get a more accurate picture of the overall soil conditions. By taking all of these factors into account, it is possible to estimate soil resistivity with a reasonable degree of accuracy. This information can then be used to design safe and effective electrical systems.